Hello PChemers, this is DW, and this is an analysis of Exam 3, the rotation vibration example or exam that we had for class. This goes over not just transitions in vibrational excitation, but also the combination of rotation with vibration, like the P&R branches, etc. As you've seen before, we have vocabulary section based upon the Quizlet study set that the class generates. Really not much discussion to go on here. Don't worry about where I've moved things around. I had too many A's on the key as it was originally generated for my key, and so then I moved things around to get some different letters to make it a little more random. So the one that you took in class had the red letters on it. And so here's the fill in the blank, so you can check your work there, but you obviously saw my comments in most cases. Let's zoom in now and look at the problems. So in the apply and analyze section of this exam, problem 1, again this was a required problem. I did all of these problems as required. There wasn't much time to come up with a variety of problems. Plus I wanted to make sure I tested these 3 exact skills. So we didn't have any options on this test. So it didn't make the test any longer to have options or longer not to have options, but got a little pushback for not having options, but that's fine. These are the skills that I really wanted to test, so I made everybody demonstrate what they knew about them. And the average was a little bit lower, so you guys need to probably work on your understanding of the material on Exam 3 because you'll see it again on the final exam. So problem 1, what's the irreducible representation of this normal mode of vibration for benzene? This revealed a little bit of misunderstanding. Many of you thought that the normal mode was just the top row, that there was only one normal mode, but no, that was a misconception. A normal mode of vibration just means a linearly independent mode of vibration. All of the vibrations are normal modes, and the normal means it sort of ties back to the concept of a normalized wave function. So every vibration in a molecule is independent from every other vibration, and those wave functions are normalized and orthogonal. So that just means that each vibration, you can call it a normal mode of vibration. And the arrows here show us about the CH stretches in this molecule of benzene. I've given you the coordinate system so that you can compare this with the character table. The z-axis is coming out of the plane of the paper. The x-axis is to the right, and the y-axis is going up. And if we look at the arrows, these 3 CH stretches are getting longer. The arrows are going out from the benzene ring, so those hydrogens are moving away from the benzene ring, and these hydrogens are moving in towards the benzene ring. The in or left to right motion cancels, and the up and down motion does not cancel. So this oscillating dipole, if we move those hydrogens out, the top of this molecule will be positive, the bottom of the molecule will be less positive, and so you'll have a dipole that's pointing down. And at some time later, these hydrogens are going to change direction and go to the other end of the molecule, and in that case, the dipole will be pointing up. And so this dipole is going to oscillate up and down, and that up and down oscillation is along the y-axis. So that means that this has Y symmetry. So this normal mode has Y symmetry. So we go to the character table for this molecule, which is not given. Okay, so you need to know what the point group for benzene is. And we did a whole lab on this, so it's pretty easy if you paid attention to the lab, that it was a D6H molecule. So that D6H character table, if we find Y on that D6H character table, it's coupled with X, but it's on a row that's E1U. And so that's the Millikan notation for this normal mode of vibration. So that's what's being asked here. What is the irreducible representation for this normal mode of vibration for benzene? So the irreducible representations of this, if you don't know the vocabulary, you can't do this problem. So the irreducible representation is labeled with Millikan notation, and that is E1U. Okay, letter B. Is this vibrational transition allowed in the IR or the Raman? If we look on that character table, it is a Y vibration, and the single order vibrations, so X, Y, Z, those are going to be IR active. And so it's in the bottom half of that character table. It has the character of X, Y, and so it's going to be IR active. not Raman active. And so then the C is what type of light will excite this transition. So for vibrational motion, the ground state, it says Y polarized light, sorry, C, what type of light will allow this transition? Since it's a Y vibration, Y polarized light will excite this vibration by absorption or emission. So if this vibration is excited and then it relaxes and drops in energy, the photon of light that comes out of the molecule will be polarized in the Y direction with respect to this molecule. To show why that's the case, we can look at the symmetry. So letter D, show how this transition is allowed using the symmetries of the transition dipole moment integral. So the intensity of the emission or the absorption is proportional to the transition dipole moment integral squared. For the ground state, for vibration, is A1G, it's fully symmetric. The excited state, for fundamental, going from V equals 0 to V equals 1, that V equals 1 state has the symmetry of the motion. So the motion is E1U, so that's where it goes here. And notice we have a fully symmetric species here, the ground state, and we have an asymmetric species here, the vibrational excitation, the motion of the molecule. And so we need to match this one. And the Y polarized light matches this E1U. So Y polarized light will excite this vibration. And so then we do the direct products. A1G times E1U is E1U. We get that from the direct product table. Now the direct product table just shows A1 and E1. It doesn't show the G and U multiplication rules. Those are separately listed on the direct product table. But GU symmetry goes like any even odd function. G times U is U. So G times U is U. And A1 times E1 is E1. Then we go to the direct product table to see what E1 times E1 is. So the direct product between two E1s is this set of symmetries, A1, A2, and E2. And then U times U is G. So each one of those has a G on it. And because this set inside this integral contains A1G, that's the top row, and that integral will be non-zero. So if the integral is non-zero, the square of that integral is non-zero, and so the intensity of that transition is non-zero. So therefore this is an allowed transition, and we can see that from the symmetry. And we don't have to do the integrals of the wave functions times the electric dipole operator of light. We can just look at the symmetries of those functions and know that this transition will be allowed, and we'll be able to emit light if it's de-excited, or we'll be able to absorb light if it's hit with the right frequency of light. Okay, problem 2. We have this set of energy levels put over here. Notice we have, let's just look at it for a little bit, we have V double prime equals 0 and V prime equals 1. We talked about in class how the first row vibrational transitions that were studied in history of science were emission, and so our primes were the initial states and our double primes were the final states. And so since they were emission, they were lines going down, so that's why the lower state values are V double prime, and then that convention just stuck. So we have the V double primes down here as the lower levels, and the V primes up here as the excited levels. We could do the same thing with the J values. So the lower vibrational energy state has these different rotational lines, 0, 1, and 2. And the upper vibrational level has these rotational lines, 0, 1, 2, and 3. And I ask you in this problem to show the following rotation and vibrational transitions and types on this energy level diagram to the right. So it starts out with a pure rotational absorption. So here it just says any pure rotational absorption. So, you know, you might be able to show this one, 0 to 1 in the excited state. I would have counted that as fine. But let's go with the ground state to the first excited state in terms of rotation. So J equals 0 to J equals 1. That's one J value. That's 1 unit of angular momentum. A pure rotational absorption would be 1 unit of angular momentum. Light coming in and the molecule absorbing that energy of that light, but also the angular momentum of that light, causing the rotational value to go up by 1 unit. So that's a pure rotational absorption. Later on, let's just skip down to H. This is a pure rotational hot band absorption. So it's still just jumping by 1 J value, delta J equals +1, but we can't start in the ground state because hot bands start in all states, not the ground state. So I have to be thermally excited to have a hot band. And so this is going from J equals 1 to J equals 2. So that's a hot band because it's starting in J equals 1, and it's pure rotational absorption because it's going up by 1 J value. Now let's get into the row vibrational transitions. So an S0 transition. So these are the criteria for an S0. This subscript 0 tells us the J double prime value. So it has to start in J double prime equals 0. And it's an S. So an S is a Raman transition, and delta J equals plus 2 for an S. So we have to have a Raman, which is a 2-photon experiment. So it's got to go up and down. The incident photon is the up, and the scattered photon is the down arrow. So starting in J equals 0, the incident photon comes in. I've got this dashed line labeled as a virtual level. So this is an electronic energy level, it's visible light, so it's in the electronic region of the absorption spectrum. And you don't want to hit an absorption necessarily, so you just want to have that photon come in and not hit an absorption, just to oscillate the electron cloud. And that's what that dashed line at virtual level is just showing you, the energy of that incoming photon. And then the inelastically scattered photon is shown here. And it comes down and hits the J value that is the initial J value plus 2. So this is J equals 0, and this is J prime equals 2. So that's an S transition. It's S0 because it starts in 0, and it's Raman because it's a 2-photon process. So there's a lot buried in this S0 transition. Let's do an O2 transition. So the O means delta J minus 2. And the subscript 2 means it starts in the J level 2 on the lower vibrational state. And it's Raman, so it's a 2-photon process. So J double prime has to be 2 for the starting point. So it starts here. We have the incident photon. We have the scattered photon, inelastically scattered. And delta J has to be minus 2. So since our initial J value was 2, our final J value has to be 0. And so that's the O2 line. And these scattered photons would be what we would detect with our detector. Okay, letter D, a Q0 transition. Now, it doesn't say Raman or infrared, so we'll just do a direct absorption Q line. So this subscript 0 tells us J double prime is 0. So we're starting here at J double prime equals 0, and delta J equals 0 because it's a Q transition. So going from 0 to 0. So we have no change in rotation, but we have 1 unit jump in vibration. So it's a row vibrational transition. The row is the J part, the vib part is the V part, and that's a row vibrational transition. It's a Q0 line because it's going from J equals 0 to J equals 0. Okay, now we could also have drawn that as a Raman Q0 line. So it could come in as an incident photon, scatter off as a scattered photon, and delta J equals 0, so that would be a Raman Q0. So either way, I would have accepted either one of those and been very pleased if you'd have done the Raman one. Then a P1 line. So the subscript 1 tells us we're starting in J value 1. It's a direct absorption because it's a P. So P, Q, and R branches are a direct absorption or emission. O, Q, S are the Raman transitions. So delta J minus 2 is O, P is minus 1, Q is 0, R is plus 1, and S is plus 2. So those are all of your delta J values for the OPQRS transitions. So a P transition is the delta J minus 1. So I'm starting in J double prime equals 1 and going up to J prime equals 0. So notice how J went down by 1 value. And V goes up by 1 because it's an absorption. And so we have the rho is a delta J minus 1, and the vib is a delta V plus 1. So that's a P1 line, direct absorption. An R1 line starts at J double prime equals 1, and then it's a delta J of plus 1. So it goes from 1, oh wow, no, see, R, well, it should go 1 to 2. So this line needs to stop right here. So I've caught my little error on my key. So R is plus 1. And so it should go from J equals 1 to J equals 2, and V equals 0 to V equals 1. So it should stop where the little hand is right there. Okay, then we have a pure rotational anti-Stokes transition. So I'm testing whether you understand what anti-Stokes means. So Stokes transitions are the inelastic scattering values where the leaving photon is redshifted from the incident photon. So notice the incident photons have longer arrows here than the scattered photons. Incident photon, scattered photon, incident photon, scattered photon. So these three are Stokes transitions. To do an anti-Stokes transition, you need to start at an excited energy level. So starting at J double prime equals 2, you have the incident photon, and then dropping down to 0, that would be an anti-Stokes transition. And it's got to jump 2 levels because the selection rules for Raman, it's a 2-photon process. So you need to either scatter away 2 units of angular momentum or absorb them in some way, but it jumps by 2 J values. O and S are delta J plus or minus 2. And so this one would be an S transition because it's got a jump of plus 2, or let's see, maybe it's a minus 2. So it might be an O. But this G, this incident photon comes in and then scatters off a blue shifted photon. So that's an anti-Stokes transition. So that's problem 2. Again, if you knew these rules here, you could have done this problem pretty quickly in drawing your lines. Now let's interpret the Rovibrational spectrum of HCl. So here's the spectrum. I've got 2 spectral lines that are labeled here. First thing to do anytime you get a Rovibrational spectrum is to look to see which is the high side and the low side in terms of the x-axis. In this case, it's plotted right to left. So on the right is 2600 wave numbers and 3100 wave numbers on the left. And so that means that this is the R branch. The high side is the R branch, the low side is the P branch. And right here would be where the Q branch would show up if we were able to have one in a diatomic molecule. So the problem is analyze this HCl spectrum to the greatest extent that you can. So I've put in all of the assignments. We start with a P1 because it's delta J plus 1. We can't start at 0 because you can't go to negative J. So starting at J equals 1, going to J equals 0, then J equals 2 to 1, 3 to 2, 4 to 3, etc. Starting at 0 for R, we're going plus 1. So this is the R branch. J equals 0 to 1. And then 1 to 2, 2 to 3, 3 to 4, etc. And so letter A, assign both branches with only the labels that are appropriate for this type of spectroscopy. So O is out, this is a diatomic, so the Q branch is out and the S is out. So P and R are the only 2 branches that are appropriate for this type of spectrum, so we're the P branch and the R branch. Estimate the vibrational frequency of the HCl stretching vibration. So you can just look at that and say, okay, this is 2850, that's 2900, so that'd be 2860, 2870, 2880 would be a pretty good estimate of that vibrational frequency. So notice in Rovibrational spectroscopy, the vibrational frequency is in the middle, and then we have some smaller vibrational energies or smaller wave number values and some higher wave number values. And it just depends upon how the J values are changing. If we're dropping in J value, those show up at a lower wave number value, and those are the P branches. And then if we have a higher, like a jump in V plus a jump in J, then those show up at a higher frequency, and those are the R branch values. But the vibrational frequency is right between those, and so this is nu 0. There's another more accurate way to calculate this. The spacing in this line is 2 times the rotational constant. And so we'll get to the rotational constant in a second. Okay? But if you look at the difference between these 2 lines, let's just do that. The difference between this P3 and the P2 line is 22.17 wave numbers. And so if we take that and we subtract it from 2843, we get to the P1. If we subtract it again, we get to this new zero line. So 2843 minus two of those gaps gives us 2887.86. So this would be a very accurate measurement of that vibrational frequency. This would be a decent estimate just by looking at it by eye. Okay, so this is a creative extension. This means it's a problem that you've never seen in this class before. You may have seen it in Gen Chem though. And that is, there are two isotopes of chlorine, 35 and 37. Which isotope of HCl is responsible for the two peaks that are labeled? Describe how you came to your conclusion on the isotopic abundance. Okay, so which peaks are labeled? These top two peaks, and look at the little doublets. These doublets are due to the two isotopes of chlorine. And so the most abundant isotope has the taller peak. The other peak is smaller because it's less abundant in the chlorine. Okay, so if we look at that, we come down here, we know that from the periodic table, the average molar mass for chlorine is 35.5 grams per mole. And that is some portion of 35 plus 1 minus that amount of 37, assuming that there's only two isotopes. Rearranging this and solving for x, we get the concentration of 35, and it's about 75% Cl35 and 25% Cl37. So you can just do the isotopic analysis, since you only have two elements, two isotopes to analyze, and you've got the average mass from the periodic table. You can solve this problem. Okay, so this is going to be the HCl35 that we're dealing with, and that will help us when we do the reduced mass. So what's the reduced mass for the most abundant HCl isotope? For diatomic, this is the reduced mass equation. And so we have 1 times 35 over 1 plus 35, or 35 over 36, which is 0.97 grams per mole. Tell me the J values for the energy levels that are connected by the two peak spectral lines. And so this one, if you look up there, we have a P2 and a P3 line that are labeled. The P2 line starts at 2 and the J value drops by 1. And the P3 line starts at 3 and the J value drops by 1. So these are the two P2 and P3 lines, and this is vibrational level 0 and vibrational level 1 up here. So it's 2 double prime and 3 double prime connected to 1 prime and 2 prime. So those are the J values for this these two peak spectral lines. Okay. Using your rotational constant and reduced mass, what is the bond length? Oh, F, what is the rotational constant using these peak values? So we come up here to find the rotational constant. This is when, I'll go ahead and speak frankly, I was really disappointed in many of the students in class. We talked in lecture quite a bit about the spacing between the row vibrational lines being 2 times the rotational constant, or 2b. And if you're doing a Raman spectrum, because it's a 2-photon process, you need a jump and a couple of J values, and the spacing between the row vibrational lines for Raman is 4b. And I even made a joke about Hamlet, and you can see that joke on some of the lectures where Hamlet asks to be or not to be. And DW says, well, the answer to that question is if it's a row vibration, it's 2b. If it's Raman row vibration, it's 4b. So, haha, that's a great joke. But people understood that from the joke that it was 2b, but then they had no clue how to use that information. So they were trying to calculate the rotational constant using the moment of inertia and the bond length and everything. Well, we don't know the bond length. We know the spectrum. So the spectrum right here is giving us the rotational constant. The difference between these two rotational lines is 2 times the rotational constant. So we just take the difference between those two rotational lines, we get this value, which is equal to 2b, like we said in class, and just divide that number by 2, and you've got b. There's your rotational constant. So it can't be easier. You've got a row vibrational spectrum, you have multiple measurements of the rotational constant. That's why this is such a precise determination of the rotational characteristics of a molecule, at least a diatomic, is because you get so many measurements of the rotational constant. So here's our rotational constant from these two lines. And we can use that to compute the bond length. So in lecture, we talked about this constant here to make life simple, where it has a Planck's constant and conversion from meters to angstroms, etc., and from the speed of light and meters per second to wave numbers, all of those different things. So we were able to come up with this constant to solve for the bond length if we knew the reduced mass in grams per mole and the rotational constant in wave numbers. So it was a straightforward calculation. Again, disappointed to see people not take advantage of some of these simplifications, but to try to do this calculation with all of the physical constants, Planck's constant, conversions, and then messing up the powers of 10. So it was a pretty big train wreck on some of these calculations because you didn't make life easy for you, and that's exactly what the slide says in lectures. Make life easy for you, combine all your constants, and come up with these shorter, more manageable equations. So putting in the rotational constant, the reduced mass, this conversion factor, taking the square root, you get our bond length for HCl of 1.25 angstroms. And then we have a creative extension. Looking at the rovibrational lines for the less abundant HCl isotope, make a case that the bond length hasn't changed with this isotopic substitution. Now the answers were pretty varied, as you might expect from a creative extension type question. Some people said, there's not much difference between 35 and 37, and that was a totally valid answer, but you're really not using the spectrum to make that case. If you look at the spectrum, what would happen if you did change the bond length? If you change the bond length, then the rotational constant would change. And if you change the rotational constant, the spacing in the peaks would change. And so the question is, if you change the isotope of chlorine, and that changed the bond length, and that changed the rotational constant, then one isotope would have a different line spacing than the other. So HCl37 would have a different spacing between its lines than HCl35. So what do we see? We see these little doublets, and we see the spacing between the short peaks is the same as the spacing between the tall peaks. And so right there is visual, that we can tell visually that there's no difference in bond length between the HCl35 and the HCl37. Because if there were, we would see a change in the spacing between these peaks. Now maybe there's a slight change, but it's not really detectable. So we can make the case that the bond length hasn't appreciably changed with isotopic substitution. Nor should it, if you think about it. We're just adding a couple of neutrons to the chlorine nucleus. That doesn't change the charges on any of the species, and the bond length is governed by the Coulombic attractions and repulsions. So if we don't change the Coulombic nature of the bond, then we shouldn't change the bond length. We'll change the vibrational frequency because the vibration depends upon the masses, but we won't change the bond length because that just depends upon the charges. So that's the rundown on Exam 3, and I'll see you around. Have a great day.